Okay, the final section in this slide is about the parameter efficient fine tuning. So what is the parameter efficient fine tuning? Or people usually use PEFT. What we learned before, it was full fine tuning. Full, as I mentioned to you, full means we will do with all the weight. We will do with updating all parameters of a model. If we do updating all the parameters, let's say you know the LLM now. In LLM, they have like 17 billion parameters. If you have 17 billion parameters, are you going to update all the parameters? If you update those parameters, the computational time will be very, very high. Okay. So the full fine tuning, these techniques adjust all weights of the model to improve performance for a specific task. Since it adjusts the entire model, because we try to do the full fine tuning, so it requires a lot of memory and computational resources. That's why there is a new concept about the fine tuning. We call it PEFT. We call this is parameter efficient. In the parameter efficient, we want to check what is the best parameter that we can use for the fine tuning. So this is the full fine tuning picture. So we are going to update all parameters. But when we use the PEFT, for example, LoRa, so we just select the important parameters and we use these parameters for the adaptation, or we call this is the adapters. And there is another kind of algorithm, QLoRa, or the quantized LoRa. So we can get the parameter, and after we have those parameters, we just leverage what is the best for your computer. After you got the best for your computer, then we will use it for the adaptation. So this is a picture to represent with the base model. The base model means what is the model that you use for building the model. Now the PEFT, it is a method for tuning. It is a method for tuning a model by updating only a specific set of parameters rather than adjusting all of the model's parameters. So only a specific set of parameters. It means we just select some of them. This provides effective performance improvement while reducing computational resources and memory usage. It means that we do not use all in order to reduce the computational resources. The PEFT, or this parameter efficient fine tuning, it frees. Okay. So if you learn from the fine tuning approach, they always use the word freeze. It means some of the parameters, if it is not important, they will freeze it. Freeze means we do not modify the weight. We will keep the weight as it is and only adjust selected parts to improve the training efficiency. So there are two prominent approaches on PEFT. The first is LoRa, or we call it low rank adaptation. And the other is QLoRa, or quantized LoRa. LoRa, or we call it, this is low rank adaptation. It is a form of PEFT that use a low rank matrix. It is to adjust the parameters in specific layers of the model. LoRa enables efficient tuning by adjusting only some parameters without updating the entire model. So we use only some parameters. So we not use all parameters. Okay, we are not using all parameters. We just use some parameters. Now let's say I have the pre-trained width. Okay. So this is the pre-trained width W, and let's assume that the W is a kind of matrix with D multiplied by D. So D refers to the dimension multiplied by D. If this one is too big, okay, it will be very hard to do the computational or the adaptation. Then we want to reduce. How to reduce it is we can select the R. Okay. R is the rank. So let's say I have this matrix. The matrix is 1000 multiply 1000. Because it is too big, then we can reduce. This is the D, this is D. So let's find the best R. Maybe let's select the rank equals to 10. Then I'm going to do the matrix multiplication. Then I will do a matrix 10,000 multiplied by 10. And then I will do another retriever 10 multiply 1000 in order to get the next hits, or this is the next layer for the modeling. So the lower rank, okay, the low rank, the purpose is for the efficient fine tuning for the large models. So if you have a big model like BERT or the new BERT like Roberta and BART, or maybe you have the open AI stuff, it is very big. We can use LoRa to fine tune, and the process is we insert the low rank matrices. So we have A and B. The advantages, it reduces the memory usage and compute costs and keep the base model parameters frozen. So this is a picture. If you are using the fine tuning, full fine tuning means you are using the all weight. So you will multiply the X in and the weight, and you will get the new H. So the X, it is a matrix. Let's say this is any F multiplied by D, and then we have the width is D multiplied by D. So we use all the width in order to produce a new head. Okay. So this is the H with the F multiplied by D. If you are using LoRa, we are not using all the weight, but instead of this weight, we want to split into two, which is A and B. So the weight itself, it will be frozen, and we are looking at the new matrix A and B that can be the best representation for this model. So we can produce one matrix and we can produce another matrix, and we can use this matrix output for the prediction. So LoRa reduces updates by focusing on rank. So we focus on this green color. Okay, so we focus on the rank. The goal is fine-tuning pre-trained models with W for a linear transformation. And let's say the pre-trained with metric is like this one. Okay, let me just make it width simple. And after that, okay, we have the learn adaptation is using A multiplied by B. Okay, so this is from this one. Okay, so we have the A and B. So this is the learn adaptation. The learn adaptation, which is from the A multiplied by B. A is a matrix size D multiplied by R. So the weight, actually, this is D multiplied by D. And we have the A. We have the A, which is D multiplied by R, where D is the size of the model original weight matrix, and R is the low rank. So the low rank is very, very small. Sometimes, maybe if you want to use only 1, then it means D multiplied by 1. If you want to use 2, then it means D multiplied by 2. It represents the direction of the chain. And B is another matrix, R multiplied by D. So it will be B R multiplied by D. It is used to scale the chain's direction defined by A. So by using this kind of matrix multiplication, we want to find the equivalent values with this W so that it is more efficient rather than do the parameter fine-tuning with all the weight. So these matrices are trainable parameters during the fine-tuning, but they are much smaller than the original weight matrix W. So we can reduce the memory and compute the overhead. Now let's suppose we have the rank of adaptation R equals to 1. This is just for the simplicity. And let's the low rank matrix for LoRa, it is initialized randomly. So this is the low rank matrix. A is 0.2 minus 0.1 and B is 0.5 minus 0.3. Okay. So if you look at this one, this is a matrix of 2 multiplied by 1, and this is a matrix of 1 multiplied by 2. And before we have the weight, which is 2 multiplied by 2. Okay. So we can generate this one randomly. After we have this A and B randomly, we want to learn the adaptation. The learn adaptation means we want to multiply A and B. So when we try to compute the adaptation delta W, it means we will check the multiplication A and B. This is the A, and then this is B. Then you know the matrix multiplication, 0.5 multiply 0.2 multiplied by 0.5, and then 0.2 multiplied by minus 0.3, minus 0.1 multiplied by 0.5, minus 0.1 multiplied by minus 0.3. And then we can get the delta W is this one. Okay, so please check if I did something wrong again. And after we got the delta W, we can update the weight, or we can update the matrix for the weight matrix. So we say this is the fine tune, the weight matrix. We want to add the W with the delta W. The delta W is from the multiplication of A and B. Then we will get a new weight. So the new weight will be from this original weight plus the delta W, and this is the new weight. It means this is the weight that has been fine-tuned, and we can use this as the model on the target dataset. Again, if you want to check this model, you can calculate the loss function. The loss function with this model, whether it is already minimized or not. If it is not minimized, then we will update the A and B. There is another kind of method for the parameter efficient fine tuning. We call it QLoRa, or quantized low rank adaptation. The QLoRa is an extension of the LoRa technique. It is to quantize the model parameters to tune them more efficiently. So the quantization, we call it quantization. It is a technique that allows model parameters to be expressed in low precision, saving memory and computational resources. So in the QLoRa, they will use the smaller model in order to do the adaptation. The purpose is to combine the LoRa with quantization. It is for more efficiency. So the quantization, it means we want to convert the weight into 4-bit precision. If you know about the computer, we have the, I think in Windows, usually they have the 64-bit. So the 64-bit means this is the number of 0 and 1 in the digital. If it is bigger, of course, it is high computational. In the common modeling, usually they use 32. In most of computers, they mostly use 32. If we use a smaller bit, of course, it is low precision. But this is good in terms of the memory. That's why they call it, this is to save the memory. So the QLoRa, they try to combine the quantization or the low memory resources with the low rank adaptation. LoRa applies the low rank adapters on top of the quantized weights for the fine tuning. So the advantages, it enables fine tuning on the GPU with limited memory. So if your computer is not that high for the memory, then you can use this QLoRa for the fine tuning. And it maintains the model performance despite quantization. Regardless the quantization, the model performance is still almost the same with the full fine tuning. So the QLoRa example, we can use the quantization in order to reduce the precision of weights to save the memory. Usually it maps the float values to integer. When you want to do the more optimized calculation, we can do like this one. So one of the technique is to map the float values to integer. So let's suppose we have the weight WQ. This is the quantized weight. The WQ is the round from the weight divided by S. S is any kind of value for the quantized. And later, after we quantize, we will dequantize. So dequantize means after, let's say, we divide with S. So we can get the original value by multiplying with S. So let's suppose we have value 10. Okay. We want to do the quantized width, and let's say S is 10. Then 10 divided by 10, it will be 1. After we have the 1 value, then we want to return it with the S, then we will do the 1 multiplied by 10. Then it will return back to the original values. Okay. Now, let's say we just make the scale S is 0.1. Now we have the matrix or the width is this one, 1.0, 0.5, 0.3, and 0.8. With the S is 0.1. So we can round the WQ and divide with the 0.1. And we can get the value WQ is this 10, 5, 3, and 8. After we quantize this one, yeah, we can get, we can do the dequantize, and we can update the dequantized value, which has been fine-tuned for the next target dataset. So this is just an example. Actually, in between this one, yeah, there is another kind of process in order to find what is the best width parameters in order to get the proper width or the updated width. The dequantized width or the W dequantized match the original W because we quantize and dequantize without adding any updates. Okay. So this one, yeah, I didn't do anything. So that's why the quantize and the dequantize, it is same. Okay. But in the real application, rounding during quantization often introduce small errors. So because the numbers that I put here is very good. In the modeling, when you have the width, the value will be like 0.00000001 maybe, or maybe some values between 0.000000. There will be very small value in the width. And because of the S or the scaling, there might be a small errors. So these small errors, it will accumulate in larger or more complex examples. So I just give you this simplification for the hand calculation, so you can understand how we can do the quantize and dequantize. But in the real world application, we want to minimize these small errors. Yeah, there are many kind of PEFT. If you want to check, you can use the Hugging Face. Yeah, this Hugging Face is now becoming a popular site for the AI and machine learning model and etc. So the Hugging Face PEFT supports many of the fine-tuning methods we discussed on the modern model out of the box. So they use you use the model GPT-2. They already perform the fine-tuning with LoRa. There's another kind of fine-tuning with prefix tuning. They also have the tuning with P-tuning. They also have another tuning with the PROM tuning. They have another kind of tuning with IA3 and so on. So there are many variants of this fine-tuning. With some manual configuration, these methods can be used with most models. So you can see the models. There are so many models now exist in the Hugging Face or in any other website. Maybe in the Python code, I will use the 1DB. Okay. So in the 1DB, it's also another kind of website to get the pre-trained model. Okay, let's take a look on this Google Colab. Some of the cell requires a lot of time. So if it requires a lot of time, maybe I will skip it. So you can try later at home. And as this morning, the computer is a little bit slower than usual days. So let me check. First, I'm going to use the data set, some of the libraries. Later, it requires the data set. So this is fine tuning with the full fine tuning. Okay, so still okay. For the full fine tuning, now I'm going to use the tokenizer from BERT. This is the BERT tokenizer. This is BERT for sequence classification. And there are some other kind of library for training arguments. Later, I'm going to get the data set from this data set. And let's just use the training test split. And we are going to predict the accuracy. Suppose we have this text. I love this movie. The film is terrible. Amazing story. Not my favorite. Now let's assume that we have the label. The first text is 1. So 1 is positive. The second is negative, 0. The third is 1. And this one is 0. Then, because this data is too small, if we split the test 0.2, maybe one data will be the testing and the other will be the training. Because we have a small data like this one, now we need to do the fine tuning. For the tokenizer, let me use the BERT tokenizer, and I'm going to use the BERT. And then for the encoding, I will encode the train text. The truncation is true, the padding is true, and let's design the maximum length is 1 to 8. So this is the maximum length for the encoding. And also the test encoding. So I need to make it the same as the training set. From the data set, I'm going to use any dictionary. The input ID, it means I'm using this data. And then I'm going to use the attention mesh. And I'm using the label. The same with the test. So the test will also need the ID and then the attention mesh and the test label. I'm going to load the full model, which is the BERT for sequence classification. This is the model. And I'm using this one. I'm calling the model which have only 2, which is the positive and negative. Now, with this training argument, I will design the model. Later, it will be in this output. And then we have the evaluation strategy with the epoch. The learning rate is this one. We have the parameter like this. And then we are going to train. So as I mentioned to you, you know already about the logics. Logics. Okay, the logic means the result, the Z, and we have the label, which is 0 or 1. And then the prediction, it will be the logics, find the maximum. Okay, from the logics, we want to find the maximum, and the maximum, it will be the prediction result. And we will check the accuracy, whether the actual label equals to the prediction or not. After that, we will do the training. Okay, so we call the model, we call the training arguments, we call the training dataset, we evaluate on the testing dataset, and we check the metrics. So fine tune for all, and then show the result. Yeah, this requires some time. So yesterday I tried this one. It requires like 2 until 3 minutes, okay, because they try to extract the bird model, and because it is the first time, so they need to get the libraries and they need to put it into this environment. So if you have a good computer, or maybe if you have the good GPU, then it may help you. Okay. I think I already set up with the GPU, so we can get this one. Okay. Now, if you can see here, the bird classification here, I'm using one of the server, which is 1DB. In the 1DB, you need to get the API. For now, it is free. So you can just register, you can just sign up. Okay. Actually, you can use also like Hugging Face. It is also free. But in the Hugging Face, there are some limitation. So the number of the data that you can use, and then how many tokens that you can use, it is limited. And I think my quota is already finished. So now I'm using the 1DB. So I will go to my 1DB account. You can sign up in this account, and then you can get the key. Yeah, like this one. So I already have the key. So in your account, later if you already have the account, try to generate the key. After you got the key, you can put it into this one, and you can run the model in your environment. Yeah, unfortunately, because our data is very small, the accuracy is 0. Okay? Because our data is only 4. So the classification is not correct. And the validation loss, the loss is very high. So you can see here, it is because of the data that we have. We have only 4 data, and all of them are not predicted correctly. This one, the full functioning accuracy is 0. Yeah, you can try with bigger data if you have the data. And that's why I always mention that when you have a very small data, it is impossible to do the classification. Even though with the fine tuning, it still didn't work properly. Now, I'm going to use another kind of fine tuning. In this case, this is a kind of fine tuning, but we are using the prompt-based fine tuning. In the prompt-based fine tuning, we are leveraging the BERT mechanism using the mask. Do you still remember mask in the BERT? In BERT, we will mask a word, and then we can predict whether this word is something related with movie or the word is not related to the movie and other things. Okay. So I'm going to use the bird again. And then I have this sentence is, this movie is Mars. Then I'm going to tokenize this sentence. I'm using the PT. And then I'm going to check the output. Again, I will get the logits, which is the Z value. And the predicted token, it will be a decoding from the logits. And I'm going to check what is the maximum. The maximum means from the result, there will be a kind of array, and we want to check where is the maximum value for this one. So the maximum will be inserted into the prompt, and what is the sentence token. The result is not that pretty good. The prompt is the movie is Mars, and the prediction is this movie is lost. Because we are not giving any task. For example, if it is about sentiment, then maybe the prediction can be the movie is good or the movie is bad. This is another kind of fine-tuning, okay, feature-based fine-tuning. Now, I'm going to show you how if we use another data set. So this example, we are still using the transformer. There is an auto tokenizer, auto model for sequence classification. And we are using the trainer and the training arguments. And I'm going to use a new data set, which is IMDb. IMDb is a review movie, a movie review. So this movie review data set, we have a number of data, and I'm going to use the first 1,000 data as the training. If you want to use all the data, of course it is okay, but I just want to limit until 1,000 because if you use all, the computational time will be higher. Okay. So let's use only 1,000, and I'm splitting the data into the train and test. So later you can check the IMDb data by yourself. And after I have those movie reviews, I will do the tokenizer. The tokenizer, I'm using the BERT. There will be also a pre-processing in order to match the path. So how many length that you want to create for the array. In this case, I'm using the 1 to 8. And after we do the pre-process, now let's do the modeling. In this case, I'm using the BERT, and let's use the number of label equals to 2. For the parameters in the BERT, I'm freezing the BERT layers. So this is the word freeze. It means when we have the parameters that requires the gradient, we set it into false. So some parameters will be frozen. And yeah, we can do with the training. Again, this is the training argument. So the parameters for the training, and we can do the training when the training data set is for the train data set, and for the evaluation, we use the testing. Again, we just train and we can check the result or the evaluation. This is also taking a little bit of time. Okay, meanwhile, we are waiting of this one. Yeah, later we can get the result. So this is the result from my previous experiment. So you can see they are downloading all the data. The data is about 20 mega. And then they generate the train and split and other things. Yeah, okay, this one, the epoch running time is quite long. Okay, you can see it requires about 6 minutes. So I will just skip this one. Later you can try. And this is the configuration for LoRa. Okay, so I mentioned to you about the LoRa fine tuning. This is the LoRa configuration. I think the upper side is the same with the previous one. We just use the BERT with the number of level 2 and we pre-train with the BERT. And for the LoRa, we can set up the configuration. For example, this is the sequence classification. The inference mode is false. Yeah, we set up the R. R means the low rank into 8. So the dropout is from the neural network dropout, and then the alpha, yeah, you can set a value like this value. And then we just use the LoRa configuration into the model. And again, I'm using the IMDb dataset. The remaining are the same, but now we are just applying with LoRa. So we put the model after we did the LoRa configuration. The remaining are the same. So the model, we are just using the model. And again, we check what is the result after we apply the LoRa. Okay, so the remaining part, it is error. So I'm still not sure what is the error. So you can skip it. Maybe I need to check later about this one. But yeah, at least you know how to run the LoRa. At least you know how to run the full fine tuning using this one. Yeah, okay, it still need like 5 minutes to finish. Okay, you can try at home for this one. Okay, I think that's all for our course. So we already did a lot of things. So today we are studying about transfer learning, fine tuning, parameter efficient fine tuning. Okay. Yeah, what you will do